Welcome. In this video, we're going to discuss something called the digit error. So in addition, this is another type of error that can occur. What happens with the digit error is you're sending a bunch of digits or symbols, they don't necessarily have to be numbers, and one of the symbols changes into another symbol. So there's no switching occurring, they're not switching places. The 0 changed into a 4. And there's no reason why it had to change into a 4. It could have changed into some other symbol. Now, to deal with the digit error, there's something called the Hamming distance that's very, very helpful. So what you do with the Hamming distance is you compare two code words that have the same length, and you compare wherever they're different. So if we have an X and a Y combination, and we're looking at the symbols that contain X and Y, we'll count every time they're different. So 1, 2, 3, 4, 5. There's 5 differences. The rest are the same. So the Hamming distance between X and Y is 5. Similarly, B and C are different. 1, 2, the Hamming distance is 2. Or 1, 2, 3, 4. There's 4 differences in that last combination. And the idea is the larger Hamming distance that you get, it will allow you to detect or correct more errors. Okay, so let's look at how do we detect digit errors. Later on, we'll move on to correcting digit errors. So the first thing that we do is design a code. So this is our language that we're designing. For example, below, we've designed some language, and then we only say things in that language when we're transmitting. So below we have what we're going to call the yes, no, and maybe code. If you're setting up a sender-receiver transmission and using the yes, no, and maybe code, that's your entire language, just 3 things in your language. So if you ever receive something outside of this code, then you know that an error has occurred because the sender will only send either that, or that. So let's look at some questions and how this might relate to Hamming distance below. So the first thing is we're going to suppose that our transmission can only corrupt up to 1 digit during the transmission. So this is very important information, and this information is a bit theoretical. Like in reality, when you're making these codes, you're never 100% sure that only one thing will go wrong. But the reality is more like you're 99.9 something percent sure that only 7 errors will occur if this much information is transmitted. So you tend to make codes that are good enough to deal with the amount of errors that are usually occurring. And every once in a while, things slip through the error detection or correction system, and you might get a scenario where you just have to restart your device because a transmission error has occurred. But for below, we're assuming that only up to 1 digit can be corrupted during the transmission. So the sender, for example, sends all 1s, and the receiver receives this. So can the receiver figure things out? Well, for part A, we're just going to ask, can they detect the error? So the receiver would say, okay, well, what is the code? The code is this, and I've received 101. 101 is not any of those options, so the error is successfully detected. Okay, so next, in this part that we just looked at, can the receiver do correction? So let's think about that. The receiver only has the information of receiving 101 and doesn't have the information of what was actually being sent. They just look in their mailbox and 101 arrives. So it could have been that one error occurred and it could have been that digit right there. That's what actually happened. But the receiver doesn't know that. It could have also been this 0 that was sent in error to produce 101. So the receiver at that point does not know which numbers were actually sent. Was it 111 or was it 001? So in this case, we can do the detection just fine, but we can't do the correction. So the receiver cannot correct back to 111 because the receiver does not know if yes was sent or if no was sent. Now, I often find that a Venn diagram is really helpful for trying to figure out and analyze and visualize what's going on with a code. So what we're going to do below is think about our code with 3 code words and draw circles around them that represent a Hamming distance of 1 away from each code word. So if you had a transmission median that would only affect up to 1 digit, this would be a nice picture to look at. And what we're going to do is corrupt every possible way so that when 111 has 1 error, that possibility ends up inside of 111's circle. And the same with all the other circles. So pause the video now and write in all of the possible errors that can occur. You should be able to write in 5 arrows and make sure you put them in the correct parts of the Venn diagram. All right, so the picture below highlights all the possible errors that can occur. So in the circles, we have all the possible 1-digit errors that can occur for each of our code words. And then notice we put 100 outside. This one really didn't fit in the description of our Venn diagram because it's a Hamming distance of 2 away from all the code words. And we wanted each circle to represent possible Hamming distances that are just 1 away. So that one was too far away. So that's a nice visualization of what's going on with the code and the errors. So something that is very, very valuable, every time you come up with a code, if you're thinking about the digit error, the number that you're really excited about getting is the minimum Hamming distance between code words. In other words, how close are the closest code words? So for this example, we can think about, well, 111 is a distance of how much away from 010? Well, it's a distance of 2 away. How about we go through all of the possibilities and then we'll report the smallest number. So this isn't really actual distance as we think of distance on our page or distance, but it's a theoretical distance, so it's nice to draw it out as an actual distance. So that distance represents 2, and the distance from the code word in the top part, the yes, and the code word for no is also a distance of 2. So that distance there is 2, if we kind of picture that on our page. And then the distance from the bottom 2 code words, the no and the maybe, that's also a distance of 2. So if we look at all 3 of those numbers and report the smallest one, that gives us the minimum Hamming distance. So in this case, the minimum Hamming distance is 2. So now let's ask ourselves some questions. So by corrupting one symbol, can you change a code word into another code word? So the answer there is no. If we just travel a distance of 1 away, so if we start in the middle of our circle and we travel a distance of 1 away, we end up inside of that circle. That will not land us on top of another code word. That is how we get successful error detection. So by corrupting 2 symbols, can we change a code word into another code word? Yeah, we can. So corrupting 2 of these 1s into 0s brings us to there. So this is where we get unsuccessful error detection. So too much can go wrong for us to do the detection. So up to how many errors can the yes, no, maybe code detect? Well, we can detect up to 1 error because we had a minimum Hamming distance of 2. And this is kind of the breaking point here when you can change the symbols and you don't get another code word, then you can still do the error detection safely. But when you corrupt enough symbols that it can change one code word into another code word, then you can no longer do the error detection. All right, so next we're going to think about error correction. So again, the sender and receiver set up a situation where they have a code that they've agreed upon. So let's say this time we just have a yes/no code to give us an example of something to work with. What we need to make sure happens to successfully design an error correcting code is we need to make sure that when an error occurs, that error could not have possibly been transmitted from any other actual code word. So this example will take us through the idea behind error correcting. So suppose the sender and receiver team experience the following error over a transmission that is known to corrupt up to 2 digits. So this time we're assuming up to 2 things can go wrong during the transmission. So for example, 111 is sent, and then the receiver gets 2 zeros and a 1. So how can we detect the error? Well, exactly the same as before. This received thing is not one of the items that are in our code, so we successfully detect the error. Okay, so can the receiver correct back to 111? Well, the receiver would have to think about, I've received 001, and the code is either all zeros or all ones. So 2 things could have gone wrong, like they actually did here. Those 2 ones could have changed into zeros. Or it's possible that this 1 here could have actually been a 0 on the sender end, and the sender could have been trying to send all zeros. Remember, it says up to 2 digits could be corrupted during the transmission. It doesn't mean that 2 digits will actually be corrupted. It could be that 1 digit gets corrupted, and then another time during a different transmission, 2 digits get corrupted. So can we correct 001 back to 111? Well, no, we can't, because we don't know if yes was sent or if no was sent. So that resulted in unsuccessful error correction, but successful detection. Okay, let's look at a different situation. So now we're going to suppose that they experience this error again. The digit error happens again, but now only up to 1 digit can be corrupted during the transmission. So this is an assumption that they know ahead of time, just up to 1 thing can go wrong. So again, the error detection can be done as before. This is not all zeros or not all ones, so we know something went wrong. Okay, so for part D, can the receiver correct this error back to 111? Well, this time we say, okay, this result is closer to 111 versus 000, and only 1 thing could go wrong. So it could not have been all zeros being sent, because if all zeros were being sent, then 2 things would have had to have gone wrong. So in this sense, the receiver can correct back to 111. And the way that we summarize this mathematically, this closeness, is with the Hamming distance. So we'll try to find the Hamming distance between the 2 possibilities. So the Hamming distance is 1 between what we received and all ones, and it's 2 between what we received and all zeros. And the idea is that the 1 is smaller. So the smaller number indicates how to do the error correction in the right way. Okay, I also find that a Venn diagram is very helpful for error detection or error correction. So let's do the same thing that we did for detection. And again, the circle is going to represent 1 thing going wrong in all possible ways. So see if you can pause the video now and draw in all 6 errors in the correct positions. Okay, so there's a nice visualization of what's going on here. We try to send this, or we try to send this, but if one thing goes wrong, it has to end up inside of that circle or inside of that circle. So for this particular code, what is our minimum Hamming distance? Well, normally you'd have to check all possible pairs and find the smallest pair, but here there's just one pair to check, just all zeros or all ones. So the distance between these two code words is 3. So that is the minimum. That's the smallest distance that you can find. In fact, it's the only distance that you can find. Okay, so let's answer some questions once we found that number. Remember how we said that this minimum Hamming distance number is the most important number that you can find when you're dealing with the digit error. So by corrupting two symbols, can you change a code word into another code word? So if you start at 0 and you corrupt one symbol, you'd end up somewhere here, and then two symbols would end up somewhere here. But remember, these aren't code words. These are errors of code words. So you cannot change a code word into another code word by only traveling a distance of 2. So the answer for part H is no. By corrupting 3 symbols, can you change a code word into another code word? Well, yeah, 3, it's a distance of 3 away, so yes, we could do the change from one code word to another. So our next question, up to how many errors can the yes-no code detect? Well, our breaking point from our no to yes was a distance of 2 versus a distance of 3. So we can detect up to 2 symbols. So it's important to indicate when we're talking about detection and when we're talking about correction. Here it was asking about detection. So our next question says, if one symbol of a code word was corrupted during the transmission, could the receiver determine which code word was sent? The receiver can assume that no more than one symbol is corrupt. So, 2 things couldn't have gone wrong. So if just one thing goes wrong, if we go back to our diagram from above and think about that, if we're starting here and just one thing goes wrong and we end up in that circle, then we're perfectly fine. We can correct it back to the center of that circle, and the same over here. That's the visualization of how error correction works. So the answer there is yes. Okay, so our next question says, if 2 symbols of a code word are corrupt during the transmission, could the receiver determine which code word was sent? This time the receiver can assume that no more than 2 symbols are corrupt. Well, if we go back to our diagram, we're saying, okay, 2 things can go wrong, and maybe the receiver has received this. Well, they wouldn't know if that came from 0 and just one thing went wrong, or if it had come from all ones and 2 things have gone wrong. So in this sense, that's where the error correction falls apart, where we can no longer do error correction. So the answer there is no. And it's in this sense that we can figure out how many errors a yes-no code can correct. When we tried it with just one error, it was perfectly fine, but when we tried 2 errors, we couldn't do it anymore. So the correction for the yes-no code in regards to digit errors is 1. The detection in regards to digit errors was 2. So now we're ready to summarize all these results in a nice theorem. So first of all, we'll summarize error detecting. So the error detecting theorem. This is a very helpful theorem if you're trying to immediately figure out how many errors your code can detect when we're talking about digit errors. So we're going to suppose up to n characters can be corrupted, so n things can go wrong. So instead of making our circle of size 1 like we did before, we're going to make our circle having a radius of n. And as long as we have every code word only as close together as this picture shows, we can get successful error detection. So notice that as long as x can't change all the way into y, as long as there's enough separation or enough Hamming distance so that that doesn't happen, we have successful error detection. So the distance that we need is a distance of n and then plus a little bit more, so n plus 1. So the magic number for error detection is n plus 1. So as long as that's less than or equal to the minimum Hamming distance, then we get successful error detection. Okay, now let's look at error correction. There's a similar theorem there. We just need our code words to be further spread out. So again, up to n characters can be corrupted. And we'll draw our picture below. This time we need a distance of 2n plus 1 between our code words. That has to be the minimum Hamming distance. So each circle represents a distance of n. So if we travel along with our pen, that's a distance of n. And then this much here is a distance of n, and we need a little bit more than that. So the distance here in between the circles is representing a distance of 1. So in total we have n plus 1 plus another n. So 2n plus 1 is the distance between these two code words. And remember that this is the closest that code words can possibly get together. So this is the minimum Hamming distance. So what we want for error correction is the number 2n plus 1 to be less than or equal to the minimum Hamming distance. If that happens, then we can successfully correct n errors. So zooming out, one last word on this. If we think about our Venn diagrams below, in the picture for error detection, what you want to make sure happens is that for each code word, its circle doesn't contain any other code word. For error correction, what you want to make sure happens, for each circle, it doesn't contain any intersection with any other circle. So that gives you a nice summary of how to deal with digit errors with detecting and correcting. Thanks so much for listening. We'll see you on the next one.